Swayam Prabha. Digital India. Educated India.
All right, so welcome to today's lecture. Today we'll talk about RSA encryption. This of course is the most famous encryption scheme. It's used literally everywhere, and this is of particular relevance to us in this course because this is the main impact that quantum algorithms have on cryptography so far. Okay, so far we have this RSA encryption which is used everywhere. There's also El-Gamal which we saw last time, which is also broken by quantum, but this is the primary one and that's what we'll study today. Okay, so to begin with, let me just recap all the things that we laid out so far so that everyone's on the same page. So if you remember, we had this this Gen RSA procedure, Gen RSA algorithm, and its role is to output a composite modulus n, capital N. Okay, so its role is to output a composite modulus n, which is the product of two primes p and q, right, and E and D such that these conditions hold. So in particular, E and D are inverses of each other mod phi of n. Alright, so we already saw this in great detail, and this is just the way to generate the modulus, the public key and the private key. Recall the RSA assumption. Okay, so the RSA assumption is going to tell us that relative to this Gen RSA procedure, there is some hard problem. So let's try to remember very precisely what the RSA assumption is going to be. So towards this, if you remember, we had defined this RSA experiment. Okay, so here basically you run the procedure from the previous slide, you get n, E and D, yeah, and then you choose a random y from Zn star and you give the adversary, any polynomial time adversary, you give this adversary n, E and y. Okay, and it is supposed to output an x such that x to the E is congruent to y in Zn star, yeah. So it is supposed to output an x such that this condition holds, alright, and if this condition holds, then we say that the output of the experiment is 1, otherwise 0. And we said that the RSA problem is hard relative to this Gen RSA procedure if for any PPT algorithm A, there is a negligible function such that the probability that the adversary outputs 1 in the above experiment is negligible. So I am going over this quickly now. All of these terms we have carefully defined, right? We have carefully defined negligible, we have carefully defined this term here, right. So we are just recapping this right now, and the RSA assumption, simply says that there is an efficient Gen RSA such that this RSA experiment or RSA problem, let's use the same notation, okay, such that the RSA problem is hard relative to it. So you see, one thing I want to say here is that even though maybe intuitively this appears not very difficult to grasp, actually there are a lot of subtleties lurking around over here, some of which we are going to see. So first of all, everybody remembers properly what the RSA assumption is and so on, right. So we did this in detail already. Now to highlight some of the subtleties that I am talking about, I'd first like to talk about, a toy encryption scheme, which is popularly known as the textbook RSA scheme. So this is what is taught in textbooks. So here what are we going to do? Okay, so we are building an encryption scheme. So what are the three procedures we need to define? There needs to be a gen, there needs to be an encrypt, which we'll just call enc, and a decrypt or dec, right? So there just needs to be this. Now what does gen take as input? Who can tell me? The security parameter, right? So we've talked about this. So then PPT or negligible, all these things are defined with respect to the security parameter, and we write it in unary. So you also remember that, because that's the size that you want to consider. So now what should gen output? It's very, very obvious. What should gen output? N, E and D, right? So it should just run the gen RSA that we saw before, right? So I'll just run gen RSA and output N, E and D such that E times D is 1 congruent to phi n. Okay, so this part is easy. Now encryption should take a public key, so that means it takes N and E, right, and it should take some message. Now the message space, what is it? Let's see. So let me ask you, what is the most intuitive way for me to do encryption based on RSA? What is the first idea that comes to your mind for computing a ciphertext? So what is hard? What is hard? In the previous slide, what did we see? The attacker is given N, E and Y and is supposed to output an X such that X to the E is Y, right? So that means that given Y, it is hard to compute X, right? So what is the first idea that we can have? Anyway, by the way, we are obviously doing this totally in reverse, right? I am giving you the assumption first and now telling you how do you use this. In real life, of course, it does not work like that. First you have a scheme and then you will prove security. Anyway, but the question still stands. So it's really important to me that all of us understand very intuitively how these schemes are being built. So what is what is the hardness being used for in any encryption scheme? So one hint is that given the public key, I should not be able to compute the secret key. That is obvious. So that is one place where hardness is being used. Another place where hardness is being used just as trivially is, given what should I not be able to compute what? Very good. Given the ciphertext, I should not be able to get the message, right? So now in the scheme that I have shown you, I mean whatever we have seen so far, we already have the public key and the secret key. This is already fixed according to our gen RSA procedure. So now the gen RSA, I mean the RSA assumption already has this N, E and D built into it. At least it has E built into it, if not D, right? So now how can I use RSA to get the second get the second hardness that I need? This is not hard. I am not asking for a proof. What is the simplest thing you can think of? Yes. So he is suggesting setting the message as the private key. So that does not work at all in any way. Why is that? Can you think and tell me? A private key is a one-time artifact of the system, right? There is one public key, one private key. I want to send thousands of messages. So why will I say I cannot set the message as the private key for that reason, point 1. Point 2 is that now we are being rigorous. So when we are being rigorous, right, we have to talk about which algorithm takes what as input and gives what as output. So now our gen algorithm is outputting the the public key and the private key, right. So, the gen algorithm, what is its input? It is only the security parameter. The key generation algorithm does not have any message. So, that is another basic syntactic reason why I cannot set the public key, I mean I cannot set the message as the private key. Nevertheless, it is a nice way of thinking. So, let us take that further. So, you have the right idea that it should be hard for me to recover the message given the private key. By the way, a third reason your proposal does not work is that I do not have a whole lot of flexibility in how I choose my private key, right. So, I mean if you remember the gen RSA procedure over here, right. So, pretty much I am given a phi of n, right, and then I am going to find an E such that the GCD is 1 and I am just going to compute the D. So, it is not that I have freedom to say whatever I want. Does that make sense? That also does not work at all. Anyone think why? So, here is there are a few different questions that I would like to ask. So, now the suggestion is that alright, maybe what I can do is I can XOR my message with my private key. Now, this also does not work for almost the same reasons that the previous suggestion did not work. So, in particular, my encryption algorithm is a public key algorithm. What are its inputs? N, E and message. Does it even have the private key? So, it cannot do that. That is point 1. Point 2 is that what you are suggesting will break completely if I have 2 messages that I encrypt. So, if I do M1 XOR D and I do M2 XOR D, then I can XOR these 2 and get M1 XOR M2, which is a complete break of security. So, I would like to remind everyone that cryptography is a deep science and this is a Turing award winning algorithm. So, we are not going to do anything totally trivial. What we have done so far has already made our life very, very simple, right, compared to the obviously compared to the invention of the algorithm. I am already giving you the assumption and just asking you to use it. So, I insist that everybody needs to try this. So far, sorry about that, thank you. So far nobody has used the RSA assumption at all. All that we have done so far is we have tried to use this public key and private key. Like first we said let us just use the private key as the message and then we said okay, let us just XOR the private key with the message. So, how are we using the RSA assumption? Everybody, we have to use the RSA assumption, right? How are we going to do that? So, the RSA assumption is that given, it is of course highlighted here, but given y in Z n star, okay, together with the public key, it is hard to compute x such that x to the e is congruent to y mod n. This is the RSA assumption, yeah. So, how are we going to use this as a source of hardness? Does everyone agree we have not used this so far? Excellent, good. That is exactly what I was waiting for. So, the simple idea is that okay, I mean so given y, it is hard for me to compute an x such that x to the e is y. So, it is very, very natural then to think of y as the ciphertext, right, and to think of x as the message, isn't it? Because you want that given the ciphertext, it should be hard to compute the message. So, this is a very natural idea. So, idea is compute m to the e mod n. Okay, and now to decrypt, so if I have, let me call this as C. I define this as, let's even make it CT to be very, very explicit. So now if I have CT and now I have the decryption key D, then how do I recover the message? Very good. So CT to the power D mod n, right? And why does that work? Because this should be m to the e times d, right, which is m to the 1 mod n, which is n, which is m. Why? Because E and D are multiplicative inverses mod phi of n, and the order of the group is phi of n. So that is what you will be wrapping around in the exponent, right. So good. So this is the most natural thing for us to try. Okay, and this also does not work. So that is why this is called textbook RSA, not RSA itself. So now who can think of reasons why this is not going to be good? By the way, here the message space we are using is Zn star in this, right, because we just want to do m to the e mod n. So now who can think of reasons why this scheme is not going to be secure? Maybe it's a worthwhile thing to remind ourselves of the security definition. So once again we did this already in great detail previously. So I've just I just have the definition stated here. So remember what this definition is. So it's called the indistinguishability under chosen plain text attack. Many of you are looking a bit blank. We did this, right? We also proved that the El-Gamal scheme is secure according to this definition. So what this definition says is that the adversary is given the public key, right? Yeah, so we'll even be looking at a sort of simpler definition than this, where we don't even need to give oracle access to the encryption procedure. But fine, so let us stick to the formal definition as stated here. What is the definition? The adversary is given the public key and it is given oracle access to an encryption procedure. So what is oracle access? Basically I can give some input and get the output. Okay. So that means that anyway I have my own public key, right. So I could certainly encrypt things on my own. I could also request the encryption oracle to give me ciphertext corresponding to messages of my choice. Finally, the adversary will output two messages M0 and M1 of the same length, okay, and then the challenger is going to choose a random bit and give an encryption of one of the two messages chosen randomly, and the attacker has to output a guess for which message is chosen, right. And the output of the experiment is defined to be 1, that is to say we say that the adversary wins if the adversary guesses the bit correctly, alright. So we said that this any scheme pi is int CPA secure if for all PPT algorithms A there exists a negligible function such that the output of this experiment is 1 with probability at most half plus negligible. Okay, everyone remember we did this definition. So when we discussed it, we in fact did not even talk about this oracle access to enc, and even for today I will, why the two are equivalent is something you might see in a homework. Very good. Yeah, so your classmate is making an important point that this experiment, by the way, I hope that everybody remembers this experiment. I mean, I put down the formal definition here because we already discussed it pretty extensively, right. Let me once again remind you that basically there is a challenger and an adversary. The challenger gives the public key. Let us forget about this oracle access to enc for a second. The adversary gives M0, M1 and the challenger gives a ciphertext of M sub B where B is random. Okay, and the adversary has to guess what B is. So, the adversary knows the ciphertext and it knows M0 and it knows M1, right. And the idea is that nevertheless it should be hard for it to guess the ciphertext corresponds to which of the two messages. So, the observation that he made is that this obviously means that the scheme has to be randomized. And why is that? So, if the scheme is deterministic, what is a trivial attack? Okay, so what you are suggesting is that if I have Oracle access to Enc, then I could get encryption for M0 and encryption for M1. In fact, it can be even simpler, right? I have the public key, so I can just compute it myself also, right? So, fine, either way works. The point is that if I know M0 and M1 and my scheme is deterministic and it is also public key, so I can also compute it myself, right, the ciphertext, then obviously I can just compute the ciphertext myself and check what the ciphertext I received corresponds to. So, for any deterministic scheme, this definition cannot be satisfied, it is trivially broken, right. And remember that this game, I would like to sort of re-emphasize this, even though we have talked about it before, that all the security games that or security definitions that we have in cryptography, which are typically game based, the reason that we define them the way we do is to capture all real world attacks as well as possible, right. So, here the idea is that basically I want to give the adversary everything that I can, I just want to hide a single challenge bit, right, and let the adversary guess based on that. Okay. So, in the real world, I mean there are sort of, in the real world I am not going to be sitting and playing this game, right. But in the real world, what kind of attacks can come about if I have a deterministic encryption scheme? Like one thing I had suggested earlier was, if we are encrypting letters of English, then we know that E is the most frequent letter. So, then I can just see in the ciphertext, which is the most frequent symbol, and I can decode that to E and so on and so forth, right. So, I can mount sort of dictionary type attacks if I have a deterministic encryption scheme. Moreover, I can do other things, like for instance, I can if I have a guess for the message, then I can compute and see if like if my message space is small, right. If I am expecting somebody to say one of 5 different things, I can encrypt them and check and see, right. Or if I have 2 data streams which are encrypted, I can compare if the underlying messages are the same or not just by comparing the ciphertext. So, there are a lot of attacks in the real world that I can mount, which are being in a very concise way captured by this definition. So, this is really important to understand and internalize that a lot of us, when we first encounter these definitions, we feel like this is such a silly definition because what challenger, what attacker, why, like students have asked me, why should we even talk to the attacker? It's a very good point, right, but you see what it is capturing here. So, the definition captures all these attacks, right, because all these attacks which I just now described are captured by the idea that the scheme is deterministic, right. And therefore, we in this definition sort of mimic that possibility by simply giving the adversary all possible messages. In fact, we say you can choose them yourself, right. So, there are only 2 messages, you know them both, right, and the only thing you do not know is the hidden bit B that I chose. So, all these attack scenarios are being captured by this definition. Okay, good. So, what goes wrong is that, well, encryption is deterministic. So, int CPA cannot be satisfied, right. A can itself M0 and M1 and test which is equal to CT. Okay.